Hello students, today I am going to start the new part of this fifth module, that is condensation and boiling. In that first part I will take, that is condensation process. The condensation is a process of the phase change. Whenever the vapor starts condensing or form conversion of the vapor to a liquid on the surface is called the condensation. And this condensation starts when the surface having the temperature lower than the saturation temperature. Even though that vapor is having the higher temperature, but the surface on which to which the vapor comes contact, that is having the lower temperature. Then when comes contact with that surface, its temperature also decreases. Vapor's temperature also decreases. Thereby, the condensation takes place. Still the temperature decreases below that one. Then that will becomes the subcooled temperatures. Subcooled whatever the temperature is there, more vapor condensation takes place, and whatever this conversion of this vapor to the liquid, that condensation takes place, that is of the two types. By the two condensation process, the condensation takes place. The first one is the film-wise condensation. In this process, the whatever the condensate is there, that wets the surface, and that will forms a liquid film layer on the surface, and that liquid film layer covers the whole surface. And as that film layer is also offers the additional resistance to the heat transfer, and thereby the heat transfer rate after the formation of the film will be reduces. And also when the surface of the condenser is having the clean, then there will be the film formation takes place. There is a film formation takes place, and that after the film formation, whatever the condensation takes place, and that process is called as a film condensation. And dropwise condensation, here when the condensate does not wet the surface, then that condensate whatever forms, those are forms as droplets on the condenser surface, and thereby that is called as a dropwise condensation. Here the whole condenser surface is not covered by the condensate. There is a droplets are formed on the surface, and thereby more surface is exposed to the vapor, and thereby the more heat transfer takes place. And in the case of dropwise condensation, the more heat transfer takes place compared to the film-wise condensation. And here if the surface is rough, and also the whatever this condensate is there, it is having the traces of the oil, then the dropwise condensation takes place. And here the whatever the condensation process is there, that condensation process, the amount of heat is transferring, and that whatever the heat transfer rate is there, that we can find out by using the heat transfer coefficient. And here the condensation whatever is there the heat transfer takes place by the convection, and for that convection up to the surface by the convection heat transfer takes place, and thereby later when it comes to the surface, the heat transfer takes place by the conduction. And if we have the heat transfer coefficient, then heat transfer rate during the condensation we can determine. And for determining that one, there is a one theory to determine the heat transfer coefficient, and thereby determining the rate of condensation, and that is the Nusselt theory of film condensation. This Nusselt theory of film condensation is considered for the vertical flat plate. Okay, for that film condensation takes place, and for that the heat transfer coefficient as well as the rate of heat transfer we have to determine. And for that the assuming the vapor is condensing on a flat vertical wall as shown in figure. This figure below figure is there, and also it is available in the data handbook. We can see that one in the condensation, this figure is available. Okay, this is vertical surface on which the condensation is taking place, and this is the x, that is the vertical direction is taken as the x, and horizontal direction is taken as the y. And this is the point where x is equal to 0, that is the starting point of the condensation. And later this delta x and the heat transfer coefficient we are going to determine, that also available in the data handbook, those we will take later. And here the x whatever is the axial coordinates is measured in the downward direction along the plate, and y is the coordinate normal to the condensing plate. The sum of the assumptions we have considered for the deriving the heat transfer coefficient by using this Nusselt theory. Those are the following assumptions are made for the derivation. The first one is the plate is maintained at a uniform temperature of TW, that is a wall temperature, and which is less than saturation temperature of the vapor Tc. That is this Tv is the vapor temperature. Okay, that wall temperature is less than that of the vapor temperature. Thereby the condensation is taking place. The second one is the viscous shear of the vapor on the liquid film is negligible at the boundary. Where the boundary, where the vapor and the film surface comes contact, there the viscous shear whatever is there, that is negligible. Then the flow of condensate downward direction by gravity is laminar. By the gravity only the condensate is flows in the downward direction, and that falls below in the collector, and that is the flow is there in the downward direction, that is a laminar flow. And linear temperature distribution exists between the wall and the vapor. Okay, here from the wall to the up to the vapor, okay, through the film whatever is there, the temperature distribution is linear. The variation of the temperature is a linear. The liquid film properties such as density, thermal conductivity, viscosity and specific heat are constant throughout the liquid film. Through the liquid film only, the whatever the heat transfer is there, that we are going to consider, and for that these properties of the liquid film are considered as a constant. The condensating vapor is clean and free from the gases and the dust. Okay, these are free from the gases and the dust, and that is condensing vapor is clean. The velocity of liquid film found along y direction is 0. Along the y direction, that's a right angle to the film thickness, the velocity is 0. Then last one, the latent heat of condensation. Okay, the heat transfer. Okay, layer is purely by conduction. Okay, the latent heat of conduction or the heat transfer takes place through the film wall is by purely conduction. That is considered. Okay, as we have the stationary film we are going to consider, that's why if it is a stationary, through the film wall the heat transfer takes place by the conduction. Let TW temperature of wall surface on which the condensation takes place. Tv or Ts saturation temperature of vapor, and rho is density of liquid film. Mu absolute viscosity of condensing liquid. And here that sketch is considered, and for that some also the considerations we have taken for the film to consider the some element to derive the heat transfer coefficient, that we will discuss later. Then HFG latent heat of vapor, K is thermal conductivity of liquid, H length, X length measured from the starting point of the film, G acceleration due to gravity, delta thickness of film. Delta is a function of X, the thickness of the film whatever this is there, that is a function of X. That is how the direction changes, this thickness also changes. Use velocity of condensate, that one in downward direction, how much velocity the movement of that film is there. Then consider an element of film. Okay, the film whatever is there, in this one element is considered. Dx at dx, this element is having the length dx at a distance of x. Then after considering that one, it is in the direction, it is having the d delta thickness in the y direction and at a distance of y here. Okay, and the total length of that one including d delta, it will become say delta. And here the force balance also we are going to consider, the shear stress that is balanced by the gravitational force which is due to its weight. Its weight whatever is there, its weight by weight whatever the downward force is acting, and this is the shear force is acting in the upward direction. Okay, then now heat is transferred from the vapor to the condensate film by convection. Then heat transferred to the plate surface by conduction. That already I told you that one. From whatever this vapor is there to that film surface, the heat is transferring by the convection, and through the film the heat transfer takes place by the conduction. Therefore, that convection is followed by the conduction. That's why the rate of heat transfer for that element dq can be written as a heat convected is equal to heat conducted. The heat convected, that is Hx, heat transfer coefficient. Hx we are going to consider as a heat transfer coefficient. Dx into 1, this is the area, surface area of the film exposed to that heat transfer. Then Tv is vapor temperature minus of the wall temperature, and that is equal to the conduction heat transfer K dx into 1 by delta. Delta is the length, okay, to that one, the length of the film to which the heat is transferring. Then this again the temperature difference by the conduction through the film, whatever is the, that is the conduction temperature, wall temperature. Then Hx is the local heat transfer coefficient, where width of the plate perpendicular is considered as a 1. Width of the plate perpendicular to the condensate is taken as the 1, that we have considered here. Then Hx, whatever is there from this equation, whatever is there, Tv minus Tw get cancels, and also the dx get cancels. Then Hx is equal to K by delta we are going to get. This equation, the first equation we are going to get, that is a K by delta or a delta x it is. Now consider the force balance of an element of thickness dx at a x between y and delta. The force I told you that one, gravitational force is equal to viscous shear force at y distance, and this is the viscous shear force mu into du by dy into dx into 1. This is the viscous shear force, and this is a gravitational force. Delta minus, that is a gravitational force is the gravitational acceleration multiplied with that mass into volume. Okay. Mass into rho AV we are going to get. The rho AV, rho is the density difference, rho A area, phi g multiplied with the distance we are going to get the, this is acceleration into that one multiplied with the distance we are going to get the velocity. Okay, then this is the this is shear force equated with the gravitational force which is acting in the downward direction. Then this, if you simplify, dx into 1 get cancels, then mu if you send that side, du by dy, this we can get g into rho l minus rho v by mu into delta minus y. Equation 2, where delta is equal to delta x is the thickness of the film. If u is equal to 0 at y is equal to 0, at y is equal to 0, at the surface the velocity is 0, and the u velocity is maximum at y is equal to delta. At the surface the maximum velocity of the film is there. Then this equation we have taken, u is equal to 0 at y is equal to 0. Then integrating to subject to boundary conditions. That equation 2, if you integrate subject to boundary conditions, that is du if you take this side and dy if you take that side, variable average the y, then u this we can take, and this term is a constant and this is a variable that we are going to get as a delta y minus y square by 2 equation we are going to get. And here the mass flow rate per unit width of the plate at any point x is given by, at any point that is a x distance, at our x distance the mass flow rate what is there, that we can have from the film element. Then mass is equal to 0 to delta rho l u dy. Okay, this distance, this we are going to get mass is equal to, then 0 to l rho l, and if you substitute u is equal to this equation, g into rho l minus rho v by mu into delta y minus of y square by 2 into dy. Then here mx is equal to, after integrating this term we are going to after integrating this delta y square by 2 we are going to get y cube by 3 here we will get, and y is equal to delta. If you substitute, this is also delta raised to cube, this is also delta raised to cube, and by taking this LCM we are going to get here delta cube by 3 we are going to get. That this term will be remain same, that is g into rho L minus rho v, and this term we are going to get as a delta cube by 3. Then that delta cube by 3 mu we are going to get here. Then now differentiating this equation 5 with the reference to delta. This if you differentiate again, because of that one, the mass flow rate, it is a total mass flow rate, and this mass flow rate for that element, particular element, if you take that is differentiation, that will gives. Then g into rho L minus rho v by mu into delta square. That is this delta cube with reference to that one. If you do the differentiation, that is the 3 delta square by 2 we are going to get. Then that 3 will be get cancelled. 3 delta square we are going to get, and 3 get cancels there. In the denominator 3 mu only we are going to get. Then this is d of delta we are going to get. The rate of heat transfer dq during the condensation of dm is the rate of with the mass flow rate, mass into this h of g, specific heat. The mass into specific heat will give the rate of heat transfer also, if you consider the specific heat and the mass flow rate. Here h of g, sorry, latent heat of the condensation. Latent heat of condensation multiplied with the this mass flow rate will use the rate of heat transfer. Then already we have the rate of heat transfer by the conduction. Okay, then according to assumption, that one this we are having. Then the dq amount, this also we have. If you equate these two, according to the assumptions, heat transfer from the film to the surface, delta is by conduction. So that this equation, conduction heat transfer equation we are having. Then now equate these two. Okay, equating these two, hm g into dm, that is dq, is k into dx tv minus tw by delta. But this dm is equal to dm, if you substitute from this equation, dm is equal to g rho L minus rho v by mu into delta square d delta. That if you substitute, dm is equal to h of g into g rho L minus rho v by mu into delta square into d delta. This is the dm, h of g into dm. Then that is equal to k dx tv minus tw by delta. Now if you simplify this equation, okay, delta cube into d delta, okay, delta cube into d delta, this delta if you multiply here, delta cube into d delta we are going to take one side, and remaining terms will take other side. Okay, the k mu tv minus tw into dx, g rho L minus rho v into h of g. Now integrating equation 9, this if you integrate to get the delta, okay, 0 to delta, delta cube d delta, then 0 to x, this term into dx, and after integrating this we are going to get delta 4 of x by 4 with reference to x we are going to take. That's why it is delta of x we have to take. Then after that, k mu tv minus tw by g into rho L minus rho v into rho L h of g we are going to get. Then dx will be, we are going to have this as a x. Then delta x is equal to 4 if you multiply this side, and this raised to 4 will take this side, that will become raised to 1 by 4. This is the local thickness of the condensate. Then from the equation 1, this equation local thickness of the condensate, whatever we got, that is substitute in the equation 1, where the heat transfer coefficient, local heat transfer coefficient is given, that is hx is equal to k by delta x. Then hx, k by delta x is there, this delta x if you substitute in this one, and after simplification we are going to get this hx is equal to g rho L minus rho v h of g k cube by 4 mu tu minus tw into x. This is the local heat transfer coefficient which is determined from the Nusselt theory of condensation. Then the average heat transfer coefficient, local heat transfer varies with the distance x raised to minus 1 by 4. This is x raised to minus 1 by 4, where is with that distance. The average heat transfer coefficient is given by Hm is equal to 1 by L 0 to L Hx dl for the length L. That can be given as a 4 by 3 Hx at x is equal to L within the distance of 0 to L. Then substituting equation 11 in 12, this Hx, if you substitute in this equation, we are going to get 4 by 3. This term, if we have, this is the average heat transfer coefficient for the vertical plate. Okay, whenever vertical plate, if you want to find out the rate of heat transfer, then this heat transfer coefficient we have to find out by using this average heat transfer coefficient. Then local Nusselt number also we can have from that one. Nusselt number is equal to hxx by k. Hx by k, that one by simplification, substituting the hx and x by k, then simplifying that one, local Nusselt number we are going to get here. And all the properties what we are considering in these equations, in the average heat transfer coefficient or local heat transfer coefficient or local Nusselt number, whatever may be, here the whatever the properties are all are there, that is a density of liquid, density of paper, hfg, k, mu, that is viscosity, x, all these we are going to find out for the average temperature. Average film temperature. Average film temperature is given as Tf is equal to Tw plus Tv by 2. And whatever these properties are there, at that temperature we have to take from the data handbook and we have to substitute here to get that average heat transfer coefficient or a local heat transfer coefficient. And this is for the vertical plate. And horizontal tube, this equation is modified, and that equation is given by as the equation is similar, that is 0.72 pi g into rho L minus rho v hfg k cube mu tv minus tw. Here instead of x we are going to substitute as the d. Horizontal tube, it is a d, we have to take that one. Comparing the equation, hf on vertical surface, horizontal surface, it will be 1.3 d by L. Then horizontal tube banks. Okay, here horizontal tube banks, number of tubes n we have to take here. That only the difference. That only hm number of n number of tubes, 0.72 pi. This term remains same. Here d is multiplied with the number of tubes n. Okay. Then Reynolds number also here it is required to find whether it is a laminar or turbulent. For that Reynolds number here we will consider that Reynolds number, that some equations for A by P, that one dynamic hydraulic diameter of the condensate flow, and that hydraulic whatever diameter is there, that also we have to use sometimes to find the Reynolds number. And Reynolds number also given as a 4 m dot by mu p, and here the p whatever the perimeter is pi d by vertical tube, outside diameter d, 2l for horizontal tube of length L, W is vertical or inclined plate. Then it is experimentally determined that one transition occurs at R is 1800. Below that one it is a laminar, above that it will be turbulent. Correlations for filmoid condensation. The filmoid condensation for the laminar flow, okay, this is a vertical surface, for that it is a 1.13 this equation, where rho v is much less than rho L. Hm can be given as 1.3, and here rho L instead of that one rho L square we are going to take. Whenever rho is much less than rho L square directly we are going to take. And for the horizontal tubes, this equation already we have discussed. Only difference is that for the vertical tube we are going to take its surface area as x distance we are going to take as a length only, and for horizontal tube we are going to take as a diameter. That difference is there, and it is a 0.925 for the vertical surface and 0.725 for the horizontal surface. It is that difference is there, and these all equations are available in the data handbook. You can see that one, delta x local thickness of condensate and local Nusselt number, average heat transfer coefficient 943 we are going to get, and for laminar flow this is 1.13 already for the if rho v is much less than rho L, for the Re less than 1800 for the laminar flow. And the properties we are going to take for this average temperature 0.5 of TW plus TV, that is the average of this one. And correlation film condensation on vertical surfaces, and local heat transfer coefficient here we are going to take for the inclined surfaces, okay. And horizontal tube, it is a horizontal tube 0.72 pi it is there, and also for the vertical the same thing we have to take, okay, 0.943, but here for the horizontal tube banks n only we have to multiply, that only the difference, okay. On horizontal inside tubes that condensation takes place, and this up to this one, okay, that equations we are going to use. Now all the equations are available. For the vertical surface it is 0.943, okay, this equation. For horizontal it is 0.725 horizontal surface, that only the difference. For the some laminar condensation 1.13, those equations we have to use, and those are required for the solving the numericals. This is enough for this one, okay. Now